Alright, in this video I'm going to go through the first review packet for the similarities unit, starting with number 1. The accompanying diagram shows two similar triangles. Which proportion can be used to solve for x? So I'm looking for consistency here, right? A big side over a corresponding small side equals another big side over another corresponding small side, or vice versa. I can do a small side over a big side that corresponds to it, or another small side is equal to another big side that corresponds to it. So the first thing I look at is I'm going to go through each of my answer choices starting with A. That's saying x over 24, so the bottom side over the left-hand side of the big triangle is equal to the left-hand side over the bottom side, so that's inconsistent. It's got to be the same proportion on each side. It's not big, small, or small, big. But for B, it's saying that big side of 24 over the side that would correspond to that in the other triangle is the 9, if I look at the placement, is equal to, and then it goes back to the small triangle, 15. Small over the corresponding side of the bigger triangle. Big over small is not equal to small over big. But if I get to choice 3, I notice that takes 32 over the corresponding 12, and then it goes back to the big triangle equals x over the corresponding 15. So that would be big over small equals big over small. So that's a consistent proportion that matches up the correct corresponding sides. For number 2, in the following diagram, BC is parallel to DE. If AB is 21, BD is 7, BC is 15, which of the following lengths is DE? Well, when I have overlapping triangles, I like to redraw them. So I'm going to draw the smaller triangle ABC. This isn't drawn to scale, but it gets the idea across. With the bottom side is 21 and BC is 15. And I'm going to draw the bigger triangle over here to the best of my abilities. That's A, D, E. And the reason I'm redrawing it is because they're overlapping, and it might be hard to notice that that entire length AD is 21 plus 7. So I'm not going to use that 7 in my proportion because that's actually not the side length of a triangle. It's just given to me to help find all of AD. And I'm looking for that ED right there. So I'm going to do a corresponding small side over a corresponding big side equals a corresponding small side over a corresponding big side. So 21 over 28 equals 15 over x. Now any proportion that when you cross multiply and multiply 15 and 28 and 21 and x is going to be a correct proportion. So even if your proportion looks a little different, but you end up at the same conclusion, that's still a correct proportion. So the missing value DE here is just 20. Number 3. A triangle has side lengths 12, 14, and 18. What is the perimeter of a similar triangle after a dilation with a scale factor of 2? So if there's a scale factor of 2, I'm just going to take each of these sides and double their length. So the 12 is going to turn into a side length that's 24. The 14 is going to turn into a side length that's 28. And the 18 is going to turn into a side length that's 36. And if I add all those together to get the perimeter, that's just going to be 88. For number 4, which of the following transformations represents a dilation? In terms of the operation you should be thinking about, you should be thinking about multiplication by a constant scale factor or division by a constant scale factor. Because division is pretty much the same thing as multiplication. Like if I'm dividing by 2 or multiplying by 1/2, that's the same effect. Now, this looks like a bump double switch, so that's not a dilation. This is just switching a sign, but you're not multiplying both of them by it. This looks like you added 3 to the 8 and added 3 to the 4, so that's not going to work. But here to get from 8 to 4, you can multiply by 1/2, and to get from 4 to 2, you can multiply by that same constant scale factor. So the scale factor to get from 8,4 to 4,2 must have been 1/2. Number 5. In the diagram below, segments AC and segment DE intersect at B. If angle D is congruent to angle E, AD is equal to 6 and ED is equal to 10 and BC is 12.5, then what is the length of AB? Well, if we take a look at this, these sides would be in proportion if the triangles could be proven similar. And remember, triangles can be proven similar by angle-angle. Now, if I look at these vertical angles, it's a pretty clear argument to say that both of these triangles have two pairs of congruent angles. So I could set up a ratio of corresponding sides, where side AD corresponds to side ED, and side AB corresponds to side BC. Try to picture it as if I were to rotate the big triangle around B, BC would line up with AB. So remember, I could either do big over small equals big over small, or small over big equals small over big. If I do big over small, a big side, or a side of my bigger triangle, is 12.5. That corresponds to x in my other triangle. I could set that equal to my other big side, 10, over the corresponding small side in the other triangle, AD. Now, like any good proportion, I could cross multiply. Multiply 12.5 times 6 along one diagonal to get 75. And 10 times x is 10x. If I divide out a 10 on both sides, I find that the length of AB I'm looking for here is 7.5. Number 6. In the diagram of equilateral triangle ABC, shown below, remember that means all three sides, AC, CB, and AB, are the same length. E and F are midpoints of AC and BC. And remember, a midpoint divides a segment into two congruent segments. So all four of those pieces are congruent because I know this is an equilateral triangle. And it says the length of EF is 2x plus 8, and AB can be represented as 7x minus 2, and they want to know the perimeter of that trapezoid on the bottom there. Well, it'd be helpful to figure out what x is first and then try to make sense of this. Recall that if two midpoints of a triangle are connected, it forms what's called a midsegment, and there's two properties of a midsegment we need to know here. One of them is that it's parallel to the side that it doesn't touch, but the more important one is that it is half the length of the side it doesn't touch. So this could be one relationship we use here, but think about if the smaller piece is half of the big piece, it's also true that the big piece is twice the length of EF. I'll move that over a little bit so it's easier to see. To me, this is an easier equation to work with because I don't have any fractions, so algebraically it might make it a little bit easier. So to find the length of AB, I can double whatever the length of EF is. And this is the equation I'm going to use to help me solve for x. So if I distribute the 2 on the right-hand side, again, I'll give myself a little bit of room over here. 2 times 2x is 4x, and 2 times 8 is 16. And let's see, I can add 2 to both sides to cancel it there. And I could subtract 4x from both sides as well. I get an equation that looks like 3x equals 18. And if I divide out the 3, I find that x is equal to 6. And anytime I solve for a variable, I like to plug it in everywhere I see that variable. So I can find the length of AB here just by doing a little bit of substitution. Well, if you're trying to think about this, you could plug it into your calculator, but 7 times 6 is 42, and minus 2 would just be 40. And 2 times 6 is 12, plus 8 is 20. Now, that should be the relationship that EF is half the length of AB because it's a midsegment. Alright, so half the battle's done here. If I'm thinking about the perimeter of this bottom trapezoid, I've got two of my sides. I've got the two bases EF and AB. The question is, how do I find those two legs, EA and FB. And the secret lies in recognizing that there is a key word here that we shouldn't forget about. This triangle is equilateral, which means all the side lengths are the same. So if I know one of the side lengths is 40, it must be the case that CB is also 40, and AC is also 40. And if E is a midpoint, each piece of that should be 20, because a midpoint divides a segment into two congruent segments. And lo and behold, I've got a trapezoid where 3 of my sides are 20, and 1 of my sides is 40. So if I add those up, 20 plus 20 plus 20 plus 40 is 100 as a perimeter. So it's the key word of equilateral, knowing what that means, and knowing a couple properties of a midsegment there. Now for a very similar problem, in the diagram below, points E and D are the midpoints of sides AC and BC. So if that's a midpoint, it's really telling you BE is a median and AD is a median as well, because it goes from a vertex of a triangle to the midpoint of the opposite side. So I'm still thinking about the 2-to-1 ratio here. What's the perimeter of triangle DEF? Well, they tell me AD is 30. And again, if I want to break that into a 2-to-1 ratio, I'm going to break it into 3 pieces by dividing it by 3. Put the smaller piece between the midpoint and the centroid. Double that, put the bigger piece between the vertex and the centroid. It tells me the whole length BE there is 24. Again, I'm going to do the same trick, where if I want to partition it into a 2-to-1 ratio, I'm going to divide it by 3, get 8, put 8 there, and 16 there. So I've got 2 sides, and they tell me that BA, or where do they say? AB is 28, right? And the relationship between this side and ED, a segment that connects the midpoints, is that it's still a 2-to-1 ratio because these triangles are similar. So I can just take half of 28 to find that the missing side length ED is 14. So when I add 8, plus 10 plus 14, that should get me my entire perimeter of 32. For number 8, which of the following statements is true? Well, again, if these triangles are similar because they both have a right angle and they share angle A, I'm looking for consistency. So let's see. I'm going to start with A. AC, a small side, over AE, its corresponding big side, all right, that looks pretty good, equals, wait a minute, AD is a side of the big triangle, so I know that's not going to work out. So that can't be true. But if I go to B, AB, a small side, over its corresponding big side AD, well, let's see, I should start with the small side again. BC, that's a small side, over its corresponding big side DE. So that must be my consistent proportion because it's small over big equals small over big. Number 9. In the diagram shown, altitude AC is drawn to BD. If AD equals 12, DB equals 16, ooh, wish I gave myself more room here, find the length of DC. Well, you need to ask yourself, it's a right triangle with an altitude dropped. So is this going to be one of those Hills proportions or one of those SAS proportions? The question you should ask yourself is, do we know any information about the altitude? Do we want to find him? Is he labeled as X? Or do we know the number of the length of AC? The answer to both those questions is no, I don't care about AC. So I'm not going to have my altitude in a proportion here. I must have a Hills proportion. So the entire hypotenuse is 16. And when I talk about my legs, your legs are on the outside of the triangle, of that big right triangle. So that's leg 1 and leg 2, as opposed to side 1 and side 2. So when I set this proportion up, my hypotenuse is 16 over one of my legs, which is 12. And now if that's the leg I use in that part of the proportion, it's the same leg in the other part of proportion. And the side that corresponds to that leg is exactly what I'm looking for. That's x. So notice leg 1 goes with side 1, and leg 2 goes with side 2, but I actually don't know any information about side 2 and leg 2, so I'm not even going to use them. Again, if I cross multiply, 16 times x is 16x. 12 times 12 is 144. And if I divide out the 16, I find that x is equal to 9. Now for something a little bit more challenging. A flagpole casts a shadow that is 160 feet long. I'm just going to sketch that picture right now. There's my shadow. We got a flagpole right there. Some sort of flag. And the entire length of the shadow is 160 feet long. At the same time, a boy who is 5 feet tall is standing 140 feet from the base of the flagpole, so that the edge of his shadow coincides with the edge of the flagpole shadow. Well, that corner is the base of the flagpole, so maybe the boy is somewhere over here, where the distance between him and that flagpole is 140 feet. In which case, the edge of both their shadows should be 20 feet, because that's just the remaining distance of that 160. 20 plus 140 is 160. And I also know that he's 5 feet tall. And the question is, find the number of feet in the height of the flagpole. Well, if you try to visualize this, these guys are actually kind of creating two similar right triangles, where if I sketch them without the pole, that big side is 160, and the man is 5 feet tall, and his shadow is only 20 feet long. So I can actually set up a proportion using this information. I could say the boy's shadow over the flag's shadow, small over big, equals the boy's height over the flag's height, small over big. So again, even though this is an application, it's still just setting up a proportion, cross-multiplying, and dividing out to find that our missing piece here is 40 feet. And that should make sense because that's bigger than the boy's height. You could always check with a scale factor, right? To get from 20 to 160, I can multiply by 8. And to get from 5 to 40, I can also multiply by 8. So that checks out that the scale factor is constant. For number 11, Mn has endpoints -8, -5, and 2, 0. Remember when you plot those points to connect them with a straight edge so that your work is as precise as possible, because it really makes a difference for these partitioning problems. Right? And I want to find a point Q such that it segments MQ to QN into a 3:2 ratio, which means I'm going to partition it into 5 pieces altogether. Now, there's an algebraic portion you could do here, but my argument is that the graphical portion is a lot easier to work with. I'm going to make this into a right triangle here with Mn as my hypotenuse. I'm going to make that horizontal distance right there between M and N, and draw up that vertical distance right there. Now, if I count the boxes, I'll call that point O, between M and O, that's actually 10 units long. And I'm going to just segment that bottom piece right there into 5 equal parts. To segment something that is 10 units long into 5 equal parts, each part should be 2 units long. So every 2 boxes, I'm going to make a tick mark. 1, 2, 1, 2, 1, 2, 1, 2. And if it's a 3:2 ratio, I go to my third one in. That would give me 3 equal parts. And 2 equal parts on the other side. I can go straight up. And there's point Q right there. So if I count where Q is, that's 2 to the left and 2 down at -2, 2. Number 12, segment CD has endpoints -14, 12 and 10, -4. Point P lies on CD at P, which is at -5, 6, and I want to find the ratio of CP to PD. So pretty much the ratio of the parts that P breaks CD up into. It doesn't really matter what this segment looks like. I'll give myself a really rough sketch just to get an idea. This point's at negative 14, 12, D's at 10, negative 4, and I don't really know where P is on this segment. If I had to take a guess just by estimating, let me try to make a nice 14 there. There we go. Maybe it's closer to C just because it's at negative 5, but I don't really know here. So I'll put P there at negative 5, 6. And I want to figure out how big CP is, right here, compared to PD. And there's two really easy ways to do that. The first way is to look at the x values and to see how much you're either going up or going down by. So to go from negative 14 to negative 5, to find the distance between those numbers, I can take negative 5 and subtract away negative 14. And it looks like I've increased 9 units from there. And if I look at my increase in my x values from P to D, 10 minus negative 5 is 15. So I've increased 15 units from there. So one way to represent this ratio would be 9 to 15. But a ratio by definition is in lowest terms, so I can divide both of those sides by 3 to find that the ratio is really 3 to 5. Now, if I didn't want to look at the x values, I could also look at the y values. To go from 12 to 6, I'd have to go down 6 units. And to go from 6 to negative 4, if I subtract those real quick, I'd have to go down 10 units. So if I compare the ratio of negative 6 to negative 10, again, I can't divide both sides by 3, but I can divide both sides by 2, where negative 6 divided by 2 is negative 3, and negative 10 divided by 2 is negative 5. Now I could also divide both sides by negative 1 to find that the ratio of the y values is also 3 to 5. So it doesn't really matter which piece you look at, but this shows that the ratio of CP to PD is in fact 3 to 5. Number 13. Given XY is perpendicular to YR and SR is perpendicular to YR, prove triangle XYZ is similar to triangle SRZ. So I'm going to make a statement column. S stands for statements and R stands for reasons. I'm going to rewrite my givens and then I'll think about how that helps me. XY is perpendicular to YR and SR is perpendicular to YR. The reason I know that is because it's given. Well, remember that perpendicular lines form congruent right angles, so I can mark a box at Y and a box at R. If I'm trying to prove two triangles are similar, my goal should be to show that they have two congruent angles. So I'm going to start with angle Y is congruent to angle R because perpendicular lines form congruent right angles. Now I'm using some abbreviations here that you can feel free to use on a test, or you can write out the words. But I still need another angle. And anytime I see two lines intersecting, I always want to look for vertical angles. So angle XZY should be congruent to angle SZR. So I'm going to label that as angle 1 and angle 2. And I'll say angle 1 is congruent to angle 2 simply because vertical angles are congruent. And that's enough to say these two triangles are similar. So I'm just going to say triangle XYZ is similar to triangle SRZ because of angle. So it's always just going to be proving two angles congruent to show that I have similar triangles. And for number 14, I'm given that FG is parallel to HG, and I want to prove some proportion is true. I want to prove that when I divide EH and EF, that's the same constant as when I divide EJ and EG. Well, remember that if my triangles were to be similar, then the sides would be in proportion. So a strategy for me is I want to prove that triangle EFG, the top triangle, is similar to triangle EHJ, and then I can just say that corresponding sides of similar triangles are in proportion. So let's try that here. I'll restate my givens. I know that FG is parallel to HJ, because that's a given. And anytime I give you parallel lines, you should be looking for congruent alternate interior or congruent corresponding. Now I notice that angle E is reflexive here. It's shared by both triangles. You could use that in your proof if you want to, but I notice that angle EFG and angle EHJ are congruent corresponding angles, and angle EJGF and angle EJH are also congruent corresponding angles. So because those are the same reason, I can lump those into the same statement, and that's actually going to save me a step in my proof. So I could say angle 1 is congruent to angle 2, and I could say angle 3 is congruent to angle 4. What's my reason for that? Parallel lines form congruent corresponding angles. And the reason I know those are corresponding, visually what I try to see is that if I take that angle and I slide it up the transversal, I translate it, it'll land right on top of the other angle. So if you notice, we've already proven two pairs of angles are congruent here. So that's enough to say that my top triangle EFG is similar to triangle EHJ by angle, and they just asked me to prove that proportion right there. So that's just one extra step to say that EH divided by EF is congruent or equal to EJ over EG, simply because corresponding sides of similar triangles are proportional. Now you'll notice that's a lot to write, so if you want to, you're welcome to use the acronym CSSTP. Just remember what that stands for. Corresponding sides of similar triangles are in proportion.